guys. So in today's video, we're going to be just continuing off on the last one and applying our knowledge to some exam style questions that you are likely to get in the actual exam. So this first question, find the general solution of the differential equation sine x dy by dx minus y cos x equals 2 sine 2x sine x, giving your answer in the form y equals fx. Now y equals fx, that's the general solution. So if you ever get a question asking you, oh, what is the general solution, you always put it in terms of y equals some function of x. Now the first thing I'm going to do is that I'm going to dress up and simplify this expression, mainly because I don't like this. I know how to work with sine 2x. I don't know how to work with sine 2x times sine x. It's a bit difficult, and we can see that there are several factors of sine x spread around the expression, so I can just divide through by sine x. So first of all, I'm going to write out the equation again. Equals sine 2x sine x. And I'm going to inform you that I'm dividing through by sine x, such that at the end I have dy by dx minus y cos x sine x equals sine 2x, because the sine x's have cancelled. And then you should realize that this is now in a form where we can calculate the integrating factor. So the integrating factor has a form of dy by dx plus some function of x, y, equals another function of x, where p in this case is the minus cos x over sine x. I always like to respect the plus here and not have to mess around with, oh, I've got a minus cos x sine x, so p should be a minus or some nonsense. Just put it in the form of plus p y and just take out this whole thing, because when you take out this whole thing, you're left with the plus y. Okay, so p therefore equals minus cos x over sine x. And we know that the integration, to calculate the integrating factor, you have to put it in the form of the exponential and the integral of p. So I'm going to put that negative on the outside, cos x sine x, sine x, then dx. Now to save space, I'm just going to come over here, and I'm just going to take a look at this integral by itself. I don't really care about the exponential right now. So the integral of cos x sine x dx. Now in my last video, I told you that one of the pointers of solving ordinary differential equations was, do you know how to integrate? And especially, do you know how to integrate trigonometric functions? This is another example, and we are going to integrate using substitution, and my substitution is going to be sine. So I'll make u the substitution of sine, and to get rid of this dx, I also create another thing that I can substitute. So du by dx equals cos x, and then I substitute into, so that I get 1 over u. And that is by far easy to integrate because it just resolves into ln u, which therefore when you substitute the sine x back into, it's minus ln sine x. Okay, so let me just draw a dash line there. So coming back here, my integrating factor is now minus ln sine x. Now, I can't cancel out the exponential and the ln unless I get rid of this minus. That's basically a minus 1 there, and with ln's, the constant in front of the ln, you can use that to power up what the ln is acting on. So that can be changed into exponential ln sine to the negative power x, and that simply becomes 1 over sine x, because sine to the negative power of 1 is just 1 over. Okay. So what do we do with our integrating factor? This is our integrating factor. What do we do with our integrating factor? We multiply everything in our original ODE expression with our integrating factor. So that is basically going to become 1 over sine x dy by dx minus y cos x over sine squared x equals sine 2x over sine x. And this is the story so far. Okay, that's the story so far. Now, remember in our last video, I also said that one of the pointers was to be able to find patterns and simplify after realizing what the pattern was, or what the not trick. I don't like mathematical tricks. It's the patterns. Math is very logical and very pattern based. Okay. I would encourage you to take a look at the left hand side always, and note that you can modify this into something else. So this 1 over sine x dy by dx can be modified into d over dx. So I just take d over dx out as the common factor, and I'm left with y over sine x. And note that you can differentiate this with respect to x using quotient rule. So quotient rule, the differential is going to be v du minus u dv over v squared. And this leads me to, if v is sine x and u is y, then v du is going to be sine x dy by dx minus u, which is y, minus y. The differential of sine x is cos x over v squared, which is sine 2x. Simplified a little bit, this is going to equal 1 over sine x dy by dx minus y cos x over sine squared x. And note that this whole thing is the same as the left hand side. They equal each other. Okay? It's the same as the left hand side, and that was made possible because this thing here is the same as the left hand side. So I can simplify the left hand side to just this exact derivative. Okay, so remember, this is an exact derivative. So the left hand side simply becomes d by dx y over sine x equals sine 2x over sine x. And this is our current story so far. Now, you knew this was coming. We have to do another integral. So let's rearrange this, and let's multiply both sides by dx, so that we've got y over sine x equals sine 2x over sine x dx integral. Okay, I'm integrating the right hand side. I don't need to integrate the left hand side because I've got no function on the left hand side that requires me to do something. I just have the dx on the right hand side. Now, I don't know how to integrate this sine 2x over sine x, but what I can do is that I can make a substitution using a trigonometric identity. Sine 2x actually equals 2 sine x cos x. So I can simplify this and turn that into 2 cos x, because when you substitute this into the sine x's cancel and you're left with the cos x. The integral of cos x is straightforward. It's just sine x. So I'm going to have y over sine x equals 2 sine x. Never forget your constant, because this is an indefinite integral. So don't ever forget your integration constant. And then the general solution, we want it in the form of, so general solution should always be in the form of y equals f of x. This isn't in the form of that, so let's do that by multiplying both sides by sine x. So y equals 2 sine squared x plus c sine x. And that is the answer to our first question. I think that is pretty straightforward, actually. For 8 marks, this is an easy 8 marks. Once you just get in the into the zone and you just remind yourself that you're being tasked on knowing how to integrate, you're being tasked on knowing how to rearrange and simplify, you're being tasked on knowing how to find patterns, i.e. the exact derivative. The only thing that you don't need to know, you just need to know how to do. And I meant what I said. You don't need to know why it makes sense. You just need to know that it's useful. It's this integrating factor. It's a whole nother video to get into why this is even a thing. Okay, so let's move on to our next question, which is 12 marks. So it's more involved, but it doesn't make it any less easier. Any less easier. So let's read out the question. Show that the transformation z minus y to the power of half transforms the differential equation dy by dx minus 4y tan x equals 2y to the power of half into the differential equation dz over dx minus 2z tan x equals 1. This kind of question is a taste of things to come, because you might find that it's easier to make a substitution like this in order for you to solve a particularly difficult looking equation. And the reason why we've done this is because we have that on the right hand side, which looks very odd. Okay, remember, if you're working with integrating factors, you need to have no functions of y on the right hand side, or no functions of your main solution on the right hand side. It needs to be a function of x or just some constant. So that's why we're actually making this substitution. So let's go ahead and do it. So show that when we make the substitution, that turns into this. The first thing I'm going to do is that, so for part A, the first thing I'm going to do is that I'm going to rewrite said transformation. And in order to get something similar to this dz by dx, I'm going to differentiate this with respect to x. Okay, I'm going to differentiate this with respect to x. And remember, because I'm differentiating this with respect to x, but y doesn't have a function of x, or is not a function of x, I'm differentiating implicitly. So differentiate implicitly. Okay, so this is, I believe, either core 3 or core 4 maths. So dz by dx simply equals a half y power to the minus half dy by dx. Okay, so that's your implicit differential. Now, because I need to substitute this whole thing into our primary equation here, let's make dy by dx the subject so that we can substitute. So make dy by dx the subject. So this goes back to my earlier point. Do you know how to rearrange? And I can make dy by dx the subject by simply multiplying both sides by 2 and dividing both sides by y to the minus a half. Therefore, we get 2 dz by dx y to the power of a half equals dy by dx. Okay, and I'm going to substitute this whole thing into that whole thing, into equation number 1. Okay, so if I just edge this down like that, actually I'm just going to rewrite equation 1 here so that I can look at it. Minus 4y tan x equals 2y to the other half. So subst into. So this whole thing becomes 2 dz over dx y to the power of a half minus 4y tan x equals 2y to the power of a half. Now, remember in the last video, I talked about certain points. One of the main points is being able to simplify. So I can simplify this by dividing everything by 2 and dividing everything by y to the power of a half. Okay. So, divide by 2 and divide by y to the power of a half. And I am left with dz dx minus 2 y to the power of a half tan x equals 1. And this is the story so far. So we're still not done yet, because part B asks us to solve this differential equation to find z as a function of x. Okay, so we've basically done most of the hard work. If you didn't realize, we've done most of the hard work by changing this inner form, which we can easily work with, because now we've got dz by dx, we've got a function of x, and we've got another function of x here. Just to make sure, that's actually meant to have disappeared. So I need to change this y to the power of a half by using our transformation. So z equals y to the power of a half. So z equals y to the power of a half. Let me get rid of this, because this is not the story so far. This is. So dz by dx minus 2z tan x equals minus 1. So this is the story so far. So another thing which is ubiquitous in every problem is to be able to spot when you've made a mistake. So when I was talking about the integrating factor, I was confused because I have dz by dx, but I didn't have z here multiplied by a function of x. I had y, and that really complicates matters. So being able to spot when you've made a mistake is very important. So part B asks us to solve this differential equation, and we've dressed it up such that we now have something easy to work with. I can find the integrating factor, because the integrating factor wants dz by dx plus p, which is a function of x, then z, equals q, which is another function of x. Now z can be y. Remember in the last question z was y. It doesn't matter. It just, so long as it follows this form, okay? And the integrating factor is therefore going to be the integral of p, and p is simply minus 2 tan x. So minus 2 tan x dx. Okay, now I'm going to step out and just focus on the integral by itself, dx, and I'm going to turn that into sine x cos x dx. So this is integration via substitution, and I'm going to make my substitution to be cos x. And to get rid of this dx, I'm going to do du by dx equals minus sine x. So when I substitute both of these into that, so subst into, I am going to end up getting 2 1 over u du, because the signs cancel and the negatives cancel, and you're just getting 1 over u, which integrates to 2 ln u, which therefore when you substitute the cos x back into, you get 2 ln cos x. So this whole thing, the integrating factor, is going to equal e to the power of 2 ln cos x, which if I want to eliminate the exponential and the ln, I just take this 2 up, so I get e ln cos squared x, and that simply becomes cos squared x. Okay, so this is my integrating factor. Now I need to take this integrating factor and multiply all the way through with it. I need to multiply all the way through with it. So at the end, I have cos squared x dz by dx minus 2z tan x cos squared x equals cos squared x. And this is currently the story so far. Now we should be looking at, there's a pattern here. There should be a pattern here. Yes, you're right. Because here, you'll find that once you go through the motion of solving it, you're going to find an exact differential. Okay? You're going to find an exact differential. And that's, we just modify this slightly to become d over dx z cos squared x. Okay, so that equals that. And we should note that we are going to solve this using product rule. So that's a u and that's a v. So my u's and v's look the same. That's a u and that's a v. So product rule. We're going to differentiate that using product rule. And that's v du plus u dv. Okay. So, let's differentiate this using product rule, where v is cos squared multiplied by du, which is going to be dz over dx, then plus u, which is z, multiplied by dv. So dv is, you differentiate this using chain rule. So that is going to be 2 Then on the inside, it's so 2 sine x, 2 sine x, cos x. Think I might have made a mistake here somewhere. So let me just take a step back for the moment. So I've got cos 2x, and I'm going to change that into cos x squared. And I need to solve this using chain rule. I'm first of all going to make a substitution. So y equals u squared. So dy by dx equals 2u. That's all right. And then my u equals cos x. So du by dx equals sine x. And to get what dy, this should be dy by du. And to get what dy by dx equals, so dy by dx equals dy by du multiplied by du by dx. So this is my du. That's my du by dx. And this is my dy by du. Okay. And so I get dy by dx equals 2 cos x times sine x. Okay. So this is actually correct. I had to step out for a minute or so just to make sure that I knew what I was doing. So the integral, the differential of v is going to be 2 cos x times sine x. So if I may just not have to go through the motion of this again, v du. So v du is going to be cos squared x times by dy by dx, and udv plus udv is going to be z, and dv is this 2 cos x times sine x. So 2 cos x sine x. You're probably wondering, hey, where's the tan? Well, 2 cos x sine x or cos x sine x actually equals tan x cos squared x, because tan x equals sine x over cos x. So when you put those two together, you just get sine x cos squared x. However, we're going to keep it in the form of tan x cos squared x, okay? So d over dx z cos squared x actually equals cos x dz by dx tan x cos squared x. So this is an exact derivative, okay? Exact derivative. So we can simplify the left-hand side to just that, okay? So the whole entire thing now becomes d over dx z cos squared x equals cos 2x. And this is the story so far. So we need to take this dx to the other side and begin to integrate. So the left hand side is cos z cos 2x, and the right hand side is going to be the integral of cos 2x dx. Now I don't know what to do or how to integrate this cos 2x. I don't know. But what I do have in my repertoire are trigonometric identities. One of the trigonometric identities I'm going to use is sine 2x plus cos squared x equals 1. And the second trigonometric identity is going to be cos 2x equals cos squared x minus sine squared x. And I'm going to find a way to get this cos squared x into something that I can work with. Okay. So I'll start with identity number 1. So identity number 1 rearranged is cos 2x equals 1 minus sine 2x, sine squared x rather. And then this sine squared x is actually identity number 2 rearranged. So this becomes cos squared x equals 1 plus cos 2x minus cos squared x. So I end up having 2 cos squareds equaling 1 plus cos 2x. Therefore, cos squared x equals a half plus a half cos 2x. And this is infinitely much more easier to integrate than cos squared x. So I'm going to have z cos squared x equals the integral of a half plus a half cos gonna have to delete that, cos 2x with respect to dx. So integration is easy. That's just going to be a half x plus a quarter sine 2x plus c equaling z cos squared x. Okay. Now we need to get it into a more general solution. So that is going to be that I divide everything by cos squared x. So z equals x over, well, let's make it easier for ourselves. So that's going to be a half x sec squared x, because 1 over cos squared is sec squared, plus sine 2x over 4 cos 2x. Now I realize I can also just do a quarter sine 2x sec squared, which I'm actually just going to go ahead and do. I'm just going to go ahead and do that. Sec squared plus c sec squared. Okay. So this is our current solution. This is our current solution. Now part C, It says, hence, obtain the general solution of the differential equation 1. So we have to go back to 1, okay? From 1, we transformed into z by using this transformation. We need to go all the way back. And we go all the way back by just saying that z equals y to the power of a half. So the general solution is remembering that z equals y to the power of a half and substituting that into. So z squared equals y. Therefore, we square everything and change it into y. So y equals everything that we wrote before. Raised to the power over 2. And this is our general solution.